Welcome to my talk, New Research for Low Resource Scenarios. I'm Jens Reimers. I work as research scientist for Hugging Face, and this is my invited talk for the Royal Holloway University of London and Cardamom for the Cardamom project. So if you look at current papers, the current hype, what you often see is like few-shot learning, state-of-the-art with just 20 examples, sometimes even zero-shot learning, or that people are able to fine-tune models in 20 seconds to get state-of-the-art sentence embeddings. In the first part of this talk, I would like to give critical overview or critical opinion about few-shot learning and low resource scenarios. And then in the second part of the talk, I want to provide some methods we're currently working on to decrease the data need for such models, especially for the field of neural search. So can we learn good models from just few hundred examples, for example? I would argue if you want a generic, widely applicable model, this is not possible. So let me explain why. So for example, imagine you have the task of matching images with text. And then I ask you which of these three images shows the Eiffel Tower. For you, it's quite simple. It's the image A. So that's a really simple task. However, if I ask you now which image shows the oak tree in Dötling, which is a small village I grew up in Germany, I assume you have like a really hard time to identify the specific oak tree I mean. But everyone who has been in Dötling, for them, it's really simple to say, okay, image B, that's the oak tree you're looking for. So what you have is a long tail in semantic relatedness. So if you plot, if you compare how many people know the relationship between two things, two objects, and you rank them, then you have on the short head, like general concept, for example, cat versus dog. Then when you go down the tail, you have at some point like C versus Java. So fewer people know what C and Java is and the relationship between these two. And then even less people know PyTorch versus TensorFlow, and less people know Roberta versus dBERT, and even less people know TSDAE versus Mirrorbird. And in general, you have an extremely long tail. So there are so many concepts in our world, facets in our world. And I argue that you need data. You must have seen an example at least once. So if you have never seen the oak tree in Dötling, there's no chance to identify it among other oak trees. When I show you 100 oak trees, you're totally lost to identify the one specific oak tree every person in the city knows. And our world is so diverse. When you think about how many animals there are, trees there are, flowers, leaves, fish, monuments, buildings, statues, natural monuments, different dishes, people, items, clothes, or different movies, drawing, arts. You need a massive data set if you want to have a model that supports all these different use cases. So even when it's sufficient to see an example only once, it still amounts to a really large data set. On the second part of this short intro, I want to talk about benchmarks. As mentioned, we have this long tail in our task, in our task, and you have to be careful what your benchmarks are testing. So what often you see is that the benchmarks are testing just the short head, so just what is common and known to everyone. However, most of the interesting applications are in the long tail. So if you only search for like Facebook and Amazon, you do not need a Google for that. I mean, if you use Google or Bing, it doesn't matter, or DuckDuckGo. It doesn't matter if you just search for Facebook and Amazon, you could even just use the bookmarks from your browser. So where the real value is in the long tail and the difficult search queries and the difficult task, where you need a lot of expertise to understand it. And sadly, our benchmarks, they are just here in the short head. So if you plot different systems on these long tail, what you often observe is like two different behaviors. So you see system A, which is like really good in what's common, like cat versus dog. but then the performance quickly drops. So it has no idea how PyTorch versus TensorFlow, what's the relationship, or what's the relationship between RoBERTa and dBERTa. And then there are systems which have fewer performance, less performance on what's really common, but they're a lot better in the long tail. However, the issue is now that that academics will optimize for the benchmark. So when your benchmark is here, academics will optimize for the benchmark. So they will optimize for system A, while for any application, obviously you want to have a system B. So what you need is a benchmark which does not only check for like the really small common thing for the short head, but which try to test the long tail. Sadly, many of the accepted benchmarks are extremely bad. So for example, one example which is used all over this year also is the SDS datasets to measure the quality for sentence embedding models. This is an extremely bad benchmark, in my opinion, for sentence embedding models because it just measures the short head. And why do we have so many benchmarks on the short head? First of all, it's easier to get data. It's also easier to annotate. You can use cheap student and crowd annotators for that. So imagine you have a search task where you want to input queries related to COVID-19, and you want to annotate relevant scientific publications for that. It's quite easy if you have a search query like COVID-19 symptoms. So you can ask some students or crowd annotators to annotate relevant publications on this. That's a lot harder when your query is from the long tail, when your query is, for example, impact of the PCV2 specific lymphocytes on CD3 plus positive T cells. To identify which publications are relevant for the second query is a lot harder. So you need domain expertise. You have to be in the field, and you cannot ask a student from computer science to annotate. While for a really generic statement like COVID-19 symptoms, you can ask any student to annotate that. So it's a lot harder to get data for the long tail. And also we need diverse long tail benchmarks. We see large performance difference on the long tail. Some models perform really well on them, others do not perform that well. And as mentioned, the value for many applications and users is in the long tail. So we should try to measure it. How good are different models in there? Further, benchmarks needs to evolve. So often we see that a field sticks to one benchmark. So one benchmark is introduced, and then people will use the same benchmark over and over again because that's how they compare to previous work. But as our models get better and as the data sets get better and larger, the benchmarks also needs to get more advanced and more difficult and more challenging. So the challenge of the long tail benchmark is that there's not one long tail benchmark you can create, but there are like a lot of different topics. So if you start with the short head, you have like the base English, like common English, like cat, dog, and so on. Then you have different topics like broader topics, sports, technology, politics. And then if you dive into one topic like technology, you have gaming, phones, AI, crypto, IoT. And the further you go down, the more specialized the topic gets, the more specialized annotators you need. And also the number of topics grows exponentially in the long tail. So an interesting question is like also how many topics is your benchmark checking? Is it like just checking, I don't know, AI, for example, from AI, scientific applications from machine learning? Or is it also checking specialized topics from gaming or specialized topics from politics where you need a lot of domain expertise? Finally, in research, we like to work on the model side. So you see a lot of papers, or most papers, they focus on the model side. And the methods get more and more advanced. So over the years, the paper get more and more complex, and the methods implemented get more and more complex. And the question is like, how big is the gain from having more and more complex training procedures? So here's a real-world example on the MS-Marco dataset. The MS-Marco dataset is a popular dataset for semantic search. You have search queries from the Bing search engine annotated with relevant paragraphs. and where you have around 500,000 pairs, so quite a big data set. And you can either train it with a really simple method on it, and you get quite good performance on the MS Micro dataset, and also quite good out-of-domain performance. So out-of-domain was tested on several different datasets. And people start to create like more and more advanced training procedures. So currently the most sophisticated method is the TSDAE method, which can improve the performance on MS Micro by 2 points and the performance out of domain by 5 points. However, what we did in July is instead to work on the training set and to collect a really large sample training data set of 200 million pairs. So this is roughly 500 times larger than the MS Micro data sets. And getting this data set was quite easy. So this was mainly roughly 5 days of work because a lot of these data sets are available, but they are in different locations. And then we trained with the most extremely simple method available, like the basic method. And we see a big improvement or small improvement on the MS Micro data set in domain by 0.5 points. However, we see a big improvement out of domain by 10 points. So it's, for this particular example, it was a lot easier to get the larger data set than to create this more sophisticated training method. So I can always recommend to work on your data and to get better and more data than try to get better training procedures. So the summary of the first part, true low resource learning is, in my opinion, not realistic. The world has too many facets, and you have to see something at least once. So if you have never seen the drawing of Mona Lisa, you have no idea how the drawing of Mona Lisa looks like. So a model will not be able to retrieve it or to classify it. Important research questions. The question is like, how can we learn unsupervised? So how can we avoid to ask human what to annotate? How can we exploit the structure in our data? So we have a lot of structure in the data. So on websites, you have, for example, the title and the body, or you have some text and some images on the websites. And also, how can we improve the data efficiency? So how can we achieve that it's sufficient for a model to see the Mona Lisa only once, one image of the Mona Lisa, and then know and be able to classify it reliably and not requiring a lot of different images of Mona Lisa. Further, we need better benchmarks. So they must evolve with training sets and models. So if the models get better and better and the training sets get better and better, they also have to get more challenging and more realistic. And I argue that they should check the long tail, like the more specialized domains. And finally, we need more data and better data sets. So improving data sets improves models often more than tuning the architecture. And for English, it's quite easy to get a lot of data, but as soon as you go to a different language, it gets a lot harder to get any good data sets. So it's any data set which is not in English is highly appreciated. So in the second part of the talk, I would like to talk about domain adaptation techniques, specifically for text embeddings and for neural search. I would like to start with an introduction into neural search and different architectures you can use to do search using neural networks, primarily transformer networks. One simple architecture is the BEIR encoder. So the BEIR encoder, you input your query and your document individually to a transformer network like BERT. And then you have some pooling operation on top of it, for example, a mean pooling of the output. And this gives you two fixed size vectors, which you have in a vector space. And then in the vector space, you look for the closest hits. So for example, you compute the cosine similarity and then find for a given query, the closest document. And you say, okay, this is the relevant document for a given query. Then there are the class of neural re-rankers. They work in a two-stage fashion. So you have some search query or some question, and then you have a first stage retrieval, which can be a BEIR encoder from the previous slide, or it can also be some BM25 lexical search, which searches the document collection. And this retrieves a set of candidates, for example, 100 candidates. And then you ask your re-ranker, the cross-encoder, to re-rank the hits and to sort the list of 100 hits to output the hits with the highest score. And the cross-encoder looks the following. So you have the input, you have the query, and you have the document. You input it to a transformer network where you have cross-attention between the query and the document. And then at the end, you get some score between 0 and 1, which gives the score how relevant is a given document for a given query. Dr. Query works on an encoder-decoder architecture. So you have some paragraphs given, and then you pass it to an encoder-decoder. So people commonly use T5 for this. And this produced some queries. So what are queries? What are questions people could ask, which they would find this document as relevant? And then you concatenate these. So for every document, you generate, for example, 40 different possible query and questions. You can concatenate them to a long document. And then you index it to your search engine, for example, Elasticsearch. And the user query arrives, the user inputs some query, and you do standard lexical search, for example. And this gives you better retrieved documents because by the predicted queries, sometimes it's predicting synonyms. It changes the word weights of the paragraph. So it identifies which words are really relevant. And the next model is Colbert. So the BEIR was a single vector approach. So the query was mapped to a single vector and the document was mapped to a single vector. Colbert is a multi-vector approach. So you have the input query and every word is mapped to a token embedding from the query and every word from the document is mapped to a token embedding. And then you compute the max similarity between one token embedding from the query to all the token embedding from the documents. And you do this for all the token embeddings in the query. And then you aggregate the scores and you get some final score between the query and the documents. So we wanted to know how good is neural retrieval. So far, papers have used a lot of training data. So often they were on MS Marco or on network questions. So NQ has 100,000 pairs, MS Marco has 500,000 pairs. And creating such large data sets, it's usually only suitable for big companies or only suitable if you have a product like Google Search, then it's quite easy to get such large data sets. But new companies, academics, and new use cases are left out because it's not realistic that academics can create a data set of 500,000 pairs easily. And so most domains, tasks, and also languages come without large training sets. So we wanted to know how well do models generalize to new domains and tasks, and how to improve the performance from unlabeled data. So these are like the two big research questions I'm currently investigating. As part of this research question, we created BEIR, Benchmarking IR. So BEIR is a diverse benchmark for information retrieval, textual information retrieval. We collected 9 different tasks and 18 different data sets for really diverse use cases. So for example, in tweet retrieval, we have some news article given and we want to find tweets talking about this news article. And in track COVID, for example, we have some COVID-19 related search query and we want to find scientific publications on this topic. So we have a lot of different diverse domains and also formulations. And then we checked a lot of different systems, how well they perform on these 18 data sets. So here we see the results, how well the model compared against BM25. So we see, for example, the combination where you take BM25 and then you apply a cross-encoder on the top 100 results to do a re-ranking. It's better than BM25 on 16 out of 18 data sets, so it's worse than on 2 data sets. On the second place is Dr. Query or Doc T5 query. It's better on 11 datasets and worse on 7 datasets. And then Cobert, it's a tie. So on 50% of the datasets, it's better. On 50%, it was worse than BM25. And then we see that the performance drops. So for example, the DPR, dense passage retrieval model from Facebook, was better on 1 dataset and on the dataset network questions where it was trained for. And on 17 datasets, it was worse than a simple lexical baseline. So BM25 plus cross-encoder re-ranking performs the best, not only on the datasets, number of datasets where we see an improvement, but also an absolute improvement. And embedding models, for example, TSDAE, ANSI, and DPR, they have issues for unknown domains. So they work well for the domains where they were trained for and the tasks they were trained for. But if the domain is really different from the training set, the performance quite drops and is often worse than a simple lexical baseline. In general, information retrieval benchmarking is quite difficult. Only a tiny fraction of query document pairs are annotated, and you assume that the other pairs are irrelevant. And often lexical model has been used to create these annotation pools. So you have some query given, you use existing tools, which are primarily lexical models, to get some candidates, and then you show the candidates to the annotator, ask which of these documents are relevant for a query, and the annotators annotate. And we were checking in our paper how many documents are the systems retrieving which have not seen by any annotator. And what we see for lexical models, for example, BM25, Doc-T5 query, or BM25 plus cross-encoder, the whole at 10 rate. So the whole at 10 rate is how many of the top 10 results have not seen by any annotator. It's quite low here. So for BM25 plus cross-encoder, just 1.6% of the hits we're retrieving have not seen by any annotator and are automatically assumed as irrelevant. For embedding models like ANSI, the rate is much higher. So it's like nearly 15%, like nearly 10 times higher than for lexical models. And what we did is we did a manual annotation of all these missing hits to see how the performance changes. And when we compute the original score, we see, for example, for ANSI, it's a bit worse than BM25. If we add these missing annotations, we see that ANSI has a lot better performance than BM25. So you should always be careful with these benchmarks and what has been annotated, what are they measuring? And as mentioned in the first part, benchmark must evolve with the models. So a lot of old benchmarks, they just used lexical models for the annotation pool because these were the primary information retrieval models available at that time. But now we have a lot of embedding models which have different properties and retrieve different hits, which are not found by the lexical models, but they suffer from the fact that these hits have not been annotated and are assumed to be irrelevant. So sadly, there's no free lunch. So what we said is that the cross-encoder and Doc-T5 query and Cobert performs really well compared to single vector embedding models, but there are downsides. So the cross-encoder, for example, has the downside that it's really slow at the inference. So if you have a GPU, you have a latency of 450 milliseconds compared to an embedding model, which has just, for example, 40 milliseconds. Cobert has the issue, it's a bit faster than the cross-encoder, but the index size is quite large, so you have large memory overhead. Doc-T5 query is quick at inference and the index is small, but it's extremely slow at indexing. So if you have to index a large corpus of millions of documents, this is like really expensive and really slow. Dense embedding models, they are efficient, but they have issues with out-of-domain data. So in the next part, I want to talk more about domain adaptation for single vector embedding models. They work well for the training data. So if the task matches a training domain, then they are fast and efficient and work well. But they have issues for out-of-domain data. And the issue is that they map sentences and queries into vector space. But if there's a new word which was not seen during training, like a new named entity, it does not know how to put this word into vector space, so where to locate it in the vector space. And in my research, I asked the question, how can you do domain adaptation without having labeled data? There are different techniques I want to present how to do domain adaptation. The most commonly known is masked language modeling, where you have a text, you masked some tokens, and then you ask your model to predict the token from the context. Then there's the work of Mirrorbird and SimCSE, concurrent work of these two, where they use multiple negative ranking laws. They input pairs, sentence one. So they input pairs and they use different dropout masks. So in a transformer network, you have dropout masks in the architecture, and they use different dropout masks for the same text. And this puts the text into similar spots in the vector space. So you get slightly different embeddings if you encode the same sentence 2 times. And then they want these 2 embeddings close in the vector space, while other embeddings should be far away. So sentence 1 should be far away from sentence 2 in the vector space. Then there's the work on contrastive tension, CT, where you have 2 models. And you present also pairs to the models if you present the same sentence. So you present sentence A to model 1 as well to model 2, then they should be close in the vector space. If you present different sentences to the 2 models, it should be far away in the vector space. Work presented by us is TSDAE. It's a denoising auto architecture. So you take some text, you add some noise. What we found works best is to delete words. So you take the text, you delete words, you pass it to a BEIR encoder, and then you do a pooling operation. So for example, you take a mean of all the BEIR token embeddings so that you have here a fixed size sentence embedding. And then you take a decoder and you try to reconstruct the text without the noise. And this here at the bottom, so you have the text with the encoder, gives you a fixed size embedding for any input text. What we also showed in the TSDAE paper is the issue when you evaluate on STS data. So all the other methods, they have been tested on STS data and shown how well they perform on the STS data. But I argue that it's an extremely bad way to evaluate unsupervised methods on STS data sets. So what we see is that STS performance on the STS data sets has near zero correlation to performance on real-world tasks. So it does not tell you anything how well will it perform for any task. And the issue is that the STS data sets has extremely simple sentences which do not require any domain-specific knowledge. And also it has quite unrealistic label distribution. So hence in the TSDAE paper, we proposed a new benchmark to evaluate unsupervised sentence embedding models using domain-specific data sets. So we use the data set from Ask Ubuntu forum, from different Stack Exchange forums, from Twitter, and from scientific publications. And then we evaluated these different models. And what we see is that masked language modeling works quite strong. So for the evaluated test, it was stronger than CT and SimCSE. And also out of the box model, which did not do any domain adaptation, just trained on NLI and STSB data, performed quite well on scientific publications. And we see some small improvement by TSDAE. So the question is like, how good are unsupervised methods? So here we have the performance of the different data sets in the unsupervised fashion compared to supervised models on different data sets. So the first was on NLI and STSB, and the second one was on MS Marco. And we see that on Ask Ubuntu, for example, even such that these models have not been trained on Ask Ubuntu specifically. The supervised models, they perform better than the unsupervised models. Similar for Stack Exchange, there the MS Marco data set is really strong. The only advantage where we see for unsupervised methods are for scientific publications, where they outperform datasets, the other datasets. So supervised pre-trained models are really hard to beat. And if you have a diverse pre-training dataset, you get great results across tasks. Like so far, unsupervised methods, they are inferior to supervised methods, which have been trained on diverse datasets. However, these unsupervised methods are interesting for pre-training. So you train on an unsupervised large corpus from your domain, and then you train supervised with some labels from your domain. So you assume you have some number of documents, some number of annotated documents. So here we have number of SciDocs, number of relevant sentence pairs. Here we have 1,000 sentence pairs. Here the dotted line is the unsupervised performance. And if we first do masked language modeling or TSDAE on a large corpus, we see quite an improvement compared to like training from scratch. And also SimCSE or CT, they are not helpful in training, in pre-training. You can also use TSDAE for domain adaptation. So you have some unlabeled data, so for example, a lot of scientific publications, and then you do the denoising autoencoder on your unlabeled data, and then you do some fine-tuning on existent supervised data, which is from a different domain, and this gives you a domain-adapted model. And we tested it in two directions. So here in the first column, we have the unsupervised results on your specific domain. Here we first trained on NLI and STS data, and then trained on, for example, Ask Ubuntu. And here we first trained on Ask Ubuntu and then trained on NLI and STS. And what we see is that this approach in the center does not work. So it sadly does not work that you first train on NLI and then STS, and then you do unsupervised training. Here the performance drops. However, if you do the opposites, where you do first unsupervised training on, for example, Ask Ubuntu, and then train with existent label data, you see quite a nice improvement compared to unsupervised training. We also tested it for semantic search. So we did unsupervised training on 6 specialized domains, and then we trained with MS Marco, and we tested for different approaches. The best approach works TSDAE, where you get a performance of 48.7. So if you do not do any pre-training, the baseline is at 44, so you get a 4.7 point improvement. And then the second best approach is inverse closed task, where you delete certain phrases from a paragraph. And then we have the other methods, MLM, CT, SimCSE, and condenser. So this is, if you're interested in this, this is upcoming work by Keixing Wang. This is also upcoming work by him on GPL, how to do domain annotation for semantic search. It uses the similar idea as Dr. Query. So you have some paragraph, Python is a high-level programming language. You pass it to your T5 system. You get an output, what is Python, like some questions or queries people could ask and where they would be happy to get this as a search result. And this creates like some silver data sets. So for all your documents you have in your domain, you generate these queries, and this gives you some silver data set on which you can then train a BEIR with. And if you do some tricks, which we will present soon in the paper, you get a really nice improvement, and the performance can improve up to between 4 and 10 points. So if you take the out-of-the-box model from MS Marco, you get a performance of 44. And then if you do these adaptation, either with GPL or do also pre-training with TSD plus GPL, can get an improvement of 51.5. So this is a 7.5 point improvement on average. A really simple and nice method. More details will appear soon in the paper. Okay, this summary about the second part. Unsupervised sentence embeddings does not work that well yet. It has often worse performance than out-of-the-box models, which were trained on diverse data. And also they quickly converge. So the authors of Mirrorbird, they put it as a big advantage in their abstract that the Mirrorbird approach converges in 20 seconds. However, if an approach converges in 20 seconds, it means it does not matter if you have 1,000 or 1 billion sentences from your domain. So the model will not be able to learn anything after these 20 seconds. And it also means it does not really learn anything new about your domain. So it does just makes the vector space a bit nicer, which improves the performance compared to out-of-the-box BERT, but it's not able to learn a lot of information from your domain. And so it's sadly not a great approach. So it's sadly not great if an approach converges quickly. So for domain adaptation, the currently best approach is to do first unsupervised training or pre-training and then do supervised training. In our experiments, the best approach was TSDAE, followed by ICT, masked language modeling, CT, SimCT, or Mirrorbird, and CD. Sadly, you have to do it first unsupervised and then supervised training. So far, it's unclear how you can take an existent model and adapt it to a new domain, which would be quite nice from a computational perspective. So this is currently an open research question, how to effectively do it, how to effectively adapt an existing fine-tuned model to your new domain. Query generation with GPL is promising. So we see really strong improvements for semantic search, and we are hoping to release the paper in the next weeks. Conclusion, work on your data. We need better data sets. So especially for languages other than English, better data sets are highly needed, and I would appreciate to see more work on better data sets and more data sets. Also work on the benchmarks. Many papers overfit with narrow evaluation on the short head. And we need diverse long tail evaluation and also improve the evaluation when model evolves. So it does not make sense to test for 10 years always on the same data set. And nowadays the pace is so high of these models, it does not make sense to test on the same benchmark for like 2 years, 3 years, but we constantly need to update our benchmarks, find better and more realistic, more challenging benchmarks to really see which models perform well and which models just overfit on the benchmarks we have. Unsupervised learning is the future. As mentioned, so far, it does not work yet that well. And you get a lot better results when you have supervised data, where you have, for example, querying relevant documents annotated. However, supervised training is hard to scale to many domains or to scale it to new domains, to other languages, because it requires a lot of effort. So big research questions I find relevant is how can we learn the most from as little structure as possible? So here we have like the different types, and it decreases with the structure. At the same time, it means we have more data. So if you have annotated data where you have a query and just an annotated relevant document, this is like a lot of structure, but you have really little data on this. You can get a lot more data when you start to mine the web. So there was a recent work where they mined Q&A pages from websites and got 140 million question answer pairs from websites in a lot of different languages. You can get even more data when you take the website title and the website body, and even more data when you just require that you work on documents, longer documents, or if you say you can work on individual paragraphs or you can work on individual sentences. And the question is like, how can we decrease the need for highly structured data? So how can we go away from annotator data and maybe go to mined data, or go from mined data to like website title body data, like data in the markup, Or how can we just work with structure in the document? So in a document, we have also a lot of structures. We have paragraphs. We know it starts at some point, and then we have some coherent story usually in documents. And how can we exploit the coherent story in the document to train good embedding models? Thank you very much. If you're interested in other talks, have a look at my websites. I put all my talks on YouTube. Also, if you're interested in the papers I mentioned, you can find them on arXiv, and feel free to contact me if you have any further questions on neural search, embeddings, domain adaptation, and so on.